What's up, everybody? Welcome to the first lecture of Calc 1. Before I get into everything that I'm going to talk about in this particular video over section 1.4, just wanted to give you all an idea of how this lecture series, how this class is going to work. Every video is going to be over either an entire section or part of a section, maybe sometimes a few sections combined. They will go over the general information within the lecture notes that I've provided you all, and really this is meant to fill in the details, the gaps, the things that you may not understand just looking straight off at the notes, right? It's going to go over that sort of material. So I want you to think of these lecture videos as supplementing the lecture notes, and the lecture notes supplementing the lecture videos. It's going to take both of them together for you to fully understand everything going on. As a result, what I would suggest for each of you is that you have the lecture notes with you while you're watching the videos so you can follow along in the lecture notes and get an idea of what it is I'm talking about. Having said all that, let's get into section 1.4. So section 1.4 is all about this idea of the secant line and the tangent line. Now, what a secant line is just a line that passes through a curve in at least two spots, just two spots. It can be more, but minimum it crosses a curve in two spots. So kind of like what we have here. We have this nice curve here that's represented as the function f of x. And then we have this straight line that goes through it in these two spots. So it cuts our function into a couple parts, right? Now, there's some questions we might want to ask ourselves about the secant line as it relates to our function. In particular, we might ask ourselves, what's this equation? What's the equation of that line? Well, to get into that, we need to review a little bit of algebra. In particular, we need to review slope-intercept form and the point-slope form. Slope-intercept form is an equation of the form mx plus b, where m is the slope, how inclined your function is, or your line is rather, plus b being the y-intercept, the spot you pass through the y-axis. Now, on the other hand, point-slope form does a few things for us. It says, let's assume we know 2 points on this line. If we know 2 points, or 1 point in the slope, then we can use the point-slope form. In particular, we care about just 1 point in the slope. That's usually how this is going to be presented. And what point-slope form looks like is this y minus y naught is equal to m times the quantity x minus x naught. Now, what is this y naught and this x naught? Happy you asked. This y naught and this x naught is the point you know, right? So maybe you have a line like this. And you're told that the slope is equal to 2, and you know the point. Let's call this the point 2, 1. You know that point has to be on the line. Well, if you wanted to get that equation back, the equation for that line, then you can use point-slope form. You can say, all right, well, I know that y minus the one y value we know is on that line, 1, is equal to 2 times the quantity x minus the x value we know is on that line. So in this case, 2. And from here, we can massage the algebra to get to what we know as the slope-intercept form. So what we're going to do is we're going to distribute this 2 all the way through and add this 1 to both sides. So let's do that now. And we still have y minus 1 is equal to, distributing that 2 all the way through, we get 2x minus 4. Adding now 1 to both sides, we get y is equal to 2x minus 3. And all we've done here is rearranged the algebra to get from point slope form to the slope intercept form of the equation for this line. That's it. Now, that's all well and good, but does it relate to secant lines? Again, I'm glad you asked. The way it relates back to the secant line is we say, well, we know we want a line that passes through this function in 2 places. We're going to call place 1 a and f of a. That's the ordered pair, right? So a is our x value, f of a is our y value for that first point. And we're going to go over some distance, let's call that delta x, to where x is now equal to a plus delta x, because that's how far away we're going, right? We're saying we're going to go from a, some distance delta x away, so a plus delta x. And that's going to correspond with the point a plus delta x, comma, our function evaluated at a plus delta x. Okay, so what all this means is that we have 2 points on our function that we know our line needs to go through. Great, awesome. We're going to use that information to find out what the slope-intercept form of that line is. The point slope, the slope-intercept form of the equation of that line, I should say. So how are we going to do that? I want you all to take a couple of seconds just to think about this on your own. So to tackle that question, what the slope-intercept form of the equation of that line looks like, let's start with a few things that we know. We know that there's going to be 2 points on this line, x1, y1, x2, y2. And we know what those 2 points are. x1, y1 is x1 equal to a, y1 equal to your function evaluated at a. In x2, y2, well, all we're doing is going delta x over, right? Some distance. And if this idea of delta x scares you right now, I'll come back to it in just a second. So hold on to that thought. I will be explaining what delta x is. But, like I was saying, x2, y2, well, x2 is just going to be a plus delta x away. Because that's, again, how far over we're going. But if that's the case, then y2 is going to be our function evaluated at x plus delta x. Okay, well, this starts to work in our favor because we have some information from point slope form in the equation of slope that we can use just to at least get everything started, to get the problem actually set up. What we're going to do is we're going to start by saying, what's the slope? Well, the slope of our equation is going to be the difference in y divided by the difference in x. So in our case, that's going to look like f of, given how I indexed everything here, f of a minus f of a plus delta x divided by, well, a minus a plus delta x is just going to be negative delta x. We've got some information that we can use now, right? We can use all of this to set up the equation of our line in point slope form. So doing that really quickly, this is going to look like choosing either x1, y1 or x2, y2 to represent our known y and x values, or x and y values. we can set this up as y minus, for simplicity, and just because it's going to look a little bit cleaner on the board, let's use this x1, y1. So y minus y1 is f of a is equal to, I'm going to leave m as just m for now, but we understand it to be all of this right here, times the quantity x minus, well, x1 is going to be a. All right. Now what are we going to do from here? We're going to do just like we did a minute ago, right? So now, working from this point slope form, we could rearrange all of this to get it back into slope intercept form. So let's see what that would look like. Well, first, we're going to distribute this m all the way through. So that's going to give us y minus f of a is equal to m times x minus m times a. Well, this thing is just a constant, right? So we could replace it if we wanted to right now. But we're going to hold on to that thought in a second because we need to bring this, or for a second rather, because we need to bring this f of a over to the other side, and that's just another constant, right? So then we'll be able to combine that with this to make one nice constant and not have to worry about a whole lot of rearranging. Or needing to use a whole bunch of notation. So to look at, or to see rather, what that looks like, we're going to get, by adding f of a to both sides, that this whole thing is mx minus ma plus f of a. But hey, everything on the very end there is one giant constant. So we could rewrite all of this to be b. We could say that b is equal to negative, or let me say, b is equal to f of a minus m of a, or m times a rather. But if we do that, that means this whole thing is just equal to y equal to mx plus b. So we've gotten this from point slope form to slope intercept form. Okay. So this is all just a bunch of math jargon, right? I'm just throwing notation at y'all. I'm not doing a whole lot of explaining just yet. Just kind of working through the algebra, such as it is. There's some things we need to talk about inside of all of this. In particular, this idea of delta and what delta is, what it means. Well, delta means nothing more than the change. So once I get this all erased, let me show you what that means. If I say delta x, all I'm saying is the change in x. So we could write x2 minus x1, right? That's it. That's all it means. Well, if that's the case, then doesn't it matter which order we do this in? No, not really. Because if we were to change the order, so let's say, let me grab some other chalk. Let's say we said that delta y now is equal to y2 minus y1, then m is equal to, well, according to that, delta y over delta x. Meaning that n is equal to y2 minus y1 divided by x2 minus x1. Now, let's play with this for a second. Let's flip the order of one of those two pairs. Let's flip the order of x2 minus x1. If we do that, then this is equal to y2 minus y1 divided by the negative of x1 minus x2. But hey, we could bring this negative upstairs to get y1 minus y2 all divided by x1 minus x2. All right, so what is it I'm getting at here? That should be your question. Well, I suppose it probably is. What I'm getting at here is that, one, it doesn't matter if you choose to represent y naught, or x naught, y naught, with this point, or this point. And two, it doesn't matter the order you take the difference of x and y, so long as you use the same order. So if you subtract x1 from x2, so x2 minus x1, then you have to have that same order in y, right? y2 minus y1. On the other hand, you could say y1 minus x2, or my mistake, x1 minus x2, but then you would need to have y1 minus y2. But you can't have them flipped, right? You can't have them crisscrossed. So you couldn't have y2 minus y1, and then in your numerator, my mistake, in your denominator, you have the other way around, right? You have to keep those indices the same. So another question might come up. What even is this secant line? What does it represent? Well, it represents the average of what's happening between these two points, right? Rather, these 2 points. It represents the average change, the average behavior. So if I were to say that a car, on average, from here to, let's say, Kansas City, drives at 60 miles an hour, well, it's understood that you're not driving the entire time at 60 miles an hour. No, part of the time you're on the interstate. You're probably doing 70, I would assume. But if you were to look at the entire trip and the time it took to get from point A to point B, that average speed would come out to be whatever that secant line is for your time travel. That is all I have to say about the secant line. So let's check out the tangent line really quick. Okay, now just to compare the two side by side, because I think that's going to be the easiest way to understand the tangent line. The secant line, we said, has to go through at least 2 points. The tangent line, on the other hand, only has to go through 1 point. 1 point on your function. And what's happening here, one way we can think of the tangent line, is we start off with a secant line, kind of like this. And we let this delta x get as small as we want. A mathematician would say arbitrarily small. We let it tend towards 0. So we take that delta x and we just shrink the value down to as small as we want it to get. So as we do, we've got A here stuck. We're just going to hold that where it's at. Then we're going to start letting delta x get small. As we do, we start moving to the left, right? So this point starts coming down something like this. And as that happens, our secant line approaches what's called the tangent line. All right, why do we care? What's so special about this tangent line? After all, this is a really weird concept, right? We're letting something get small. So it's like a variable is changing, but not, but kind of? That's a weird idea. Why do we even care about this? Well, we care about it because look at this tangent line here. This line in green. You get really close to that point, to the point of your function with which your tangent line is tangent to. So we say that our tangent line, t of x, is tangent to f of x at a f of a. Well, if we get really close to that point, so if we get in the ballpark of x equal to a, so for those points really close, or for those x values really close to a down here, it's really hard to tell the difference between our tangent line and our function. And for that reason, it's sometimes more convenient to talk about your tangent line than it is to talk about the actual function. Because, yeah, it's an approximation, but it looks like a pretty good approximation for a relatively large set of x values, right? And this is why we care about tangent lines, because they can make the math easier for us. So, for example, engineers. There is a method that you will oftentimes use. There's a couple of different methods you'll use. Newton's method, there's some linearization methods that do just this. Instead of caring about your function, because that thing may not be nice to work with, why don't we instead care about our tangent line, and only for a collection of x values? That's why we care about the tangent line. But in order to get to this place of the tangent line, and being able to talk about it, we need to come back to an idea that I just hinted at with this delta x. Letting this delta x get small requires a very particular tool, a new tool that we have not seen before in all of mathematics up until calculus. It is what all of chapter 1 is about. This new tool is called the limit. We're going to talk more about the limit in the next video, but just as a motivating thought, as motivation for why we even care about the limit, well, it lets us get from the secant line to the tangent line. And the tangent line oftentimes gives us some really good tools that just make the problem easier to work with sometimes. Another motivation for why we need the limit is to talk about what's called the derivative, which is used when talking about tangent lines. So I'm kind of obscuring it a little bit here. In particular, I'm not explaining how we get the equation of the line for the tangent line. We'll get to that. We'll get to that in a couple lecture videos. But just as a motivation, like I said, we care about the tangent line because it lets us approximate things about our actual function in a way that may sometimes be easier for us. And we care about this idea of the limit because it lets us calculate this idea of the derivative. And the derivative is going to tell us a lot. One thing it will allow us to do is to find the equation of that tangent line. So having said that, that is all I have for this lecture. If you'll have any questions, feel free to shoot me an email. As of making this video right now, do not know when my office hours will be, but I will try to post that sometime before Monday. That is my plan. Having said that, have a good one, everybody.